Hi everybody, we are still going to be in 4.1 today. We're talking about spans and subspaces. All right, first thing we want to do is remember what in the heck is a span? Okay, and let's remember the span is the set of all linear combinations of a set of vectors. Okay, and we are going to start with an example. And that's basically what almost this whole video is going to entail. Okay, we are going to show that the span of the following vectors, 1, -1, 3, 2, 1, 0, is a subspace of R3. So we need to show that it satisfies those three conditions that we talked about in the last video. So we need to check that the 0 vector is in H. So let's just make a little note up here and call this span H. We need to check is the 0 vector in H, and then is it closed under addition and multiplication. Okay, and let's call this vector v1 and this vector v2. Okay, so is a 0 in H? So basically what's that asking is 0 a linear combo of v1 and v2? And remember, a linear combination, right? Take this vector, and you scale them. And what we want to know is, can we get 0? So how can I fill in those scalars to make that a true statement? I'm going to pretend that people said, scale them both by 0. And that's right. Right now we've taken the 0 vector and we've written it as a linear combination of our two vectors. Okay, so we've got, yes, the 0 vector is in H. Okay. So let's think about a couple of other things here. 0 vector is in H. And now let's think about 2. Is it closed under addition? Okay. So we need to take two generic vectors. I'm going to say U and W, B and H, and we want to show that U plus W is in H. And remember, right, U and V are going to be linear combinations of V1 and V2. Okay, so that means that whenever we have U plus W, well, U is some linear combination of V1 and V2. So we could write it, say, as A V1 plus B V2. And then W is some other linear combination. So maybe that's C V1 plus D V2. And the goal here is to get to U plus W in H. So what we need to do here is to transform this into a linear combination of V1 and V2. So we need it to look like something times V1 plus something times V2. And the way we're going to do that is by using our vector space properties. Okay, so let's rearrange this. Whoops. Let's rearrange this and put the V1 parts together, and then the V2 parts together. And now what are we going to do, right? The goal is to get it like a V1 term and a V2 term. So let me give myself a little more room. Okay. the goal is to figure out what goes here, what goes here. And basically we're just taking this V1 and we're factoring it out or kind of undistributing it. So A plus C is left here, B plus D is left there, and that's just based on the structure of vector space, we're allowed to do that. And then this is in that span, right? Span is all linear combinations that fit this bill, right? Scalar times V1, scalar times V2, that fits the bill, so it's an H. So we're good to go. All right. And now let's talk about, is it closed under, forgot a letter there. Is it closed under scalar multiplication? So this time we're going to let C be a scalar in R. We're going to let U be an element of H. And then we want, right, we're going to look at CU, okay? And let's just remember here, right, this is a linear combo of our vectors. So when we go down here and write it out, U is some linear combination of our vectors, where A and B are real numbers. And the goal, right, we want CU to be a linear combination of V1 and V2. We want to show it's also in that span. So what we're going to do is just distribute that C, CA, V1 plus CB, V2, and now it exactly fits that bill. Okay, so there we go, right? So therefore, the span of those vectors V1 and V2 is a subspace of R2. Great. And you might have noticed, right, in the calculations that we did here, I never actually used what V1 and V2 were. It didn't really matter. It just mattered that they were vectors in R2. And that turns out to be, right, this is a thing that's always going to happen. Okay, so we have theorem 4.1.1, which basically says that spans are always subspaces. I'm not even going to write it out in the technical way. It just says that spans are always subspaces. Okay. And let's see here. There's one other thing that I want to talk about, which is sort of a convenient way to write out spans. Let me, okay. Okay, let's do one more example here. Okay, so let's let W be all vectors of the form, say A minus B, B plus 2D, and A plus C. Okay, where A, B, C, and D are, nope, not in R4. There's 4 of them, but they are all real numbers. Okay, and what I want to know is I want to find a set of vectors that spans W, or show that W is not a vector space. Okay, so what we're going to do here, you want to be thinking about, like, if I add together 2 vectors that just generically look like this, am I going to get back 2 vectors that always look like this? And one way to sort of break that up and see is right? We can take this vector, okay, and we're going to kind of take it and do something that looks a lot like parametric vector form, which we've talked about before. So break it up into the A piece, the B piece, the C piece, and the D piece. And then now what we've got is, right, these we can, just like we would with variables when we're solving, we could bring that A out. We could bring the B out. We could bring the C out. And we could bring the D out. Okay. And you might be asking, why is this really nice for us? And the reason it's really nice is we started with a generic vector in W, and what we did here was we wrote it as a linear combination of 4 vectors, right? Each of these terms is vector times scalar, vector times scalar. So anything in here is a linear combination of 4 vectors, which means that W is a span of these vectors, or rather is the span of these vectors. So we don't actually have to prove any of the subspace things because W is the span, and spans are subspaces. That was our theorem. So W is a subspace, or it is a vector space in and of itself. Great. Let's talk for a second about what types of things kind of ruin it being a subspace. Okay. Okay, and now we're going to show something like this. So let's say A plus B, A, and then 5. Where A and B are real numbers, we're going to show that this is not a vector space. So the main thing that's different, I mean, we only have 2 sort of placeholders here, A and B, and that's fine. But the main thing that's different is we have this component down here, which is just a 5. Okay, so we can, that 5 is going to kind of screw things up for us. So we can see, all right, if I have a vector here that looks like this, and let's say I have another generic one that's that same format, right? The sum of 2 numbers and then the other one. What's going to happen is I'm going to get, okay, A plus C plus B plus D, and the second component is going to be A plus C. So I'm looking good so far, right? It's a number plus a number, and then the first part of the first component and the second component are the same. And then what happens down here, I get 5 and 5, which is 10. Okay, right? But to be in my space, that has to be a 5. This is decidedly not 5. So this thing that we got by adding them together is not V. It's not closed under plus, which means that it's not a vector space. All right.